Let's focus on computing some integrals where we have trig functions. Our first example is going to motivate the discussion for the rest of this video. Let's take the integral of sine cubed x dx. It looks pretty straightforward and simple, but it turns out to be rather difficult. Let's see. My first naive approach might be to say, aha, I know how to integrate things raised to the third power. That's just going to be sine of x to the fourth times 1/4 and plus c. And I'm done. I just raise the power and I multiply by the reciprocal. This is incorrect, right? And why is it incorrect? It's because it ignores chain rule. That if I were to go backwards and take the derivative of this, I would see that the 4 would cancel with the 1/4, so it would be sine of x, but I would have to worry about chain rule and multiply by the derivative of sine of x, which is cosine x, which isn't in here. So maybe I'll put a line through that we know that you can't just use power rule when you have a function on the inside. Wouldn't it be nice if we had a u substitution, if there was maybe some cosine lurking in here so that we were able to do this? Because as it stands, we aren't able to use any of the rules that we've done so far. So what can we do to this to be able to get that cosine for a u substitution? We're going to make use of some trig identities. So I'm going to use the fact trig identity. I know that sine squared x plus cosine squared x is equal to 1, and that just comes from Pythagorean theorem. And that means that I can rearrange this and rewrite this original integral as the integral of sine squared times sine. And then I can write, because this is just sine cubed, that's 2 sines multiplied by each other times another sine multiplied. And I'm going to rewrite this Pythagorean identity as sine squared x equals 1 minus cosine squared x by subtracting cosine from each side and doing a substitution. So that means that I'm left with 1 minus cosine squared x times sine of x dx. Now, why is this helpful? This looks a lot more complicated than what we had to start with, but it turns out now we have a u sub that we wanted. There are a couple of different approaches to finish off this problem, and I'll show you each of them. One is to start and just do the u sub right here. So I'm going to set u in this case is going to be equal to my cosine function, because the derivative of cosine is sine, and I can make use of that. So I'm going to let u equal cosine of x, and then du is equal to negative sine of x dx. And I can convert these pieces in this integral. So that means that my integral is equal to 1 minus u squared, and the sine x dx, I need a negative to get my du from this negative sign. This is something that's really easy to integrate. I can use polynomial rule. The integral of this is equal to u. Well, I have a negative on the outside, so I want to keep track of that. A negative on the outside, the integral of 1 is u, and the integral of negative u squared is negative 1/3 u cubed. And I can distribute that minus sign and see that I get 1/3 u cubed minus u plus c. I probably should have had a plus c in that last step as well. So notice that we used a trig identity and pulled out something that would be our u to be able to integrate this. We could have done the u substitution in 2 steps, and this is something that I'll highlight quickly, that I could distribute this and I get the integral of sine of x minus cosine squared x sine of x dx. And I would still have to use a u substitution. I could just break this into 2 separate integrals. The integral of sine of x is negative cosine of x, and the integral here, I would have to use the same u substitution that I did here. Oh, and this solution will end up with the same solution that we had here, which is 1/3. What was my u in this case? Cosine of x cubed minus cosine of x. Sorry, that's a little crooked. So that's one way to solve this particular problem. Let's look at another example, and then we'll generalize what we've found. So in this next example, we don't have sines and cosines. We have tangent cubes and secants to the fourth. This looks sort of overwhelmingly complicated at first glance, but I'm going to remind us of a couple of facts, and that'll make this a little bit easier. So the first fact that I want to remind us of is the derivative of tangent is secant squared. So if I were to set u equal to tangent of x, then I would know that my du would have to be equal to secant squared x. So I see some tangents and some secants. That's one thing that I might keep in mind. Or if I were to set the other order and let u equal secant squared x, secant x, sorry, the derivative of secant is secant tangent, secant x times tangent x. So these are derivative facts that you should know from your previous calculus class, or you might want to look up at a table to refresh yourself. So this is one thing that I'm keeping in mind, that I know I'm going to want to pull out something to be my u. Like if I let u be equal to tangent, then the du, I see that I have a secant to the fourth here. Maybe I can make use of that. Similarly, maybe if I set u equal to secant, maybe I have some secant tangents to work with. The other fact that I'm going to make use of is just something based on what we saw before, that sine squared x plus cosine squared x equals 1. This is a trig identity I want you to memorize. And if I were to take this identity and divide everything by cosine squared x, why would I do that? It gives me a new trig identity, and this is one that I don't have memorized, but it's easy to memorize if you just think of dividing our original function by this. Sine squared divided by cosine squared is tangent squared. Cosine divided by cosine is 1, and 1 over cosine squared, that's just secant squared. So here's another trig identity, as well as some derivative facts that we're going to use to be able to solve this problem. So you could memorize a bunch of rules. Instead, we're going to use some ingenuity to try to figure out what we want to do. I'm thinking to myself, if I pull out a secant squared to act as my du, I would need to convert everything else into tangents. Let's see if we can do that. So let's approach this problem by pulling out a secant squared factor. So that leaves us with a secant squared x. I'm breaking up my secant to the fourth into 2 secant squareds. And I'm thinking to myself that one of those I want to leave as my u. And this other one, I want to convert into tangents. And thankfully, I have this identity that can do exactly that. So this leaves me with tangent cubed x times tangent squared x plus 1 times secant squared x dx. Notice I haven't done any integration. There's no calculus. All I've done is trig substitution. And in my final step, I say, aha! Now I can apply this clever u substitution. If I let u, maybe I should do it in this order, if u is equal to tangent of x, then du is equal to secant squared x, and I have dx, and I have this secant squared dx sitting right there. So that means that this becomes, u is tangent of x, so this becomes u to the third times u squared plus 1 times secant squared x dx becomes my du. Maybe I shouldn't have parentheses there. And this, again, is something that we know how to integrate. So I'm going to multiply through. Notice I cannot integrate each piece, but I'm not allowed to say, aha, this is the integral of 1/4 u to the fourth times 1/3 u cubed plus u by taking the integral of this chunk and the integral of this chunk. That does not work. Why does that not work? Well, you can verify by taking the derivative of this and seeing that it doesn't line up. Instead, I'm going to have to distribute this so that they're actually polynomials, and I get u to the fifth plus u cubed du And when I integrate this, I get 6 u to the 6th plus 1/3 fourth u to the 4th plus c. Sorry, I'm being a little messy. And then I can plug in my original u, which is tangent of x, and I get 1/6 times tangent of x to the 6th plus 1/4 tangent of x to the 4th plus c. So let's summarize some of the things that we just talked about. How do we go about solving these trig integrals? So if I have some integral and it has a bunch of messy trig stuff in it, what do? We want to isolate a single du factor and then convert the rest of the factors into u's using trig identities. So that's one method. Or sometimes you just need to simplify what's going on. So you might want to break up tangent into sine over cosine, for example. That might be something that allows you to convert into trig identities in a way that you didn't see before. And also there are a number of trig identities that might make something complicated be a little more simple. So here is a helpful list of some u and du values. This is actually just a table of derivatives of our trig functions. So for example, in the first problem, I let u equal cosine, and so my du was negative sine. And in the second problem, I let u equal tangent, and so my du was secant squared x. But usually you're looking over to see what du's do you have to work with, and then try to work backwards to see if I can convert the rest of the stuff into what the u looks like. Here's some trig identities that you might use. So you have memorized sine squared plus cosine squared equals 1. And like we saw, if you divide everything by cosine, you end up with this identity. And if you divide this whole top thing by sine squared, you end up with this identity. So these bottom two are things I don't memorize. I just memorize the first one and then do helpful division. But these over here are other possible identities that are helpful. Let's say I have a cosine squared by itself and 1 minus sine squared just isn't cutting it. Then here are some ways that we can convert those as well. So let's look at one more problem. It's maybe a little bit trickier. So in this problem, I have cosine to the 6x sine squared x dx. And we're clever. We want to be able to make use of some of our u substitutions, right? That's one of the helpful things that I might think of. So let's try this out by setting maybe sine equal to u. This is going to be our try number 1. And I'm going to go through a couple of failed tries before we get to the right try, because really this is something that's more of an art than a procedure. You can memorize a bunch of procedures, but there are so many different cases that it becomes overwhelming. Instead, I think trying different ideas gives you a better feel of what to do. But we know, we have some intuition that if I let u equal, let's say, cosine of x, then what's my du equal to? It's going to be negative sine of x dx. And what happens to this function then? We already have a bunch of cosines here, and we can pull out one of the sines, but unfortunately, maybe this is another naive approach. Maybe I say, aha, well that means that this is equal to the integral of u to the 6th, and if du is negative sine, well this is just sort of like du squared, right? Because I have two sines there. But du squared, that doesn't make sense. That doesn't work. I can only have one of the du terms, so let's not do that. Instead, let's pull out just one of the sine squareds. So I'm going to make this negative and have cosine to the 6th x times sine of x times negative sine of x dx, because now this whole chunk is my du and my cosine is my u, but then I have this extra sine piece left over that there's really nothing I can do with, and it comes from the fact that this sine is raised to an even power. So this method of this u isn't actually going to work. Let's try another method and flip-flop them. Let's let u equal to sine x and du equal to cosine x dx. And we see that we run into a similar problem. I'm going to pull out just one of the cosines so that I can get my du. So then I'm left with cosine to the 5th x times sine squared x times cosine x dx, because together the cosine of the 5th and the cosine would make the cosine to the 6th. So this can become my du. My sines are u's, and I need to convert cosine to the 5th into sines, because I need to have everything in terms of sine. And it turns out this also isn't going to work, because I can only deal with it when I have sine or cosine squared and not cosine to the 5th. I could have cosine squared squared, or maybe cosine squared squared squared, but cosine to the 5th is not going to work. So we need to get more clever. So what's our final piece of clever? I'm going to look at our hint sheet, see if there's something in here that can help. And it turns out that maybe this is the way to go. That if I turned my sine squareds or my cosine squareds all into the same sorts of things, then I would be able to do this. Or maybe I could use my sine of 2x times this to be able to do